heavily involved with CySER as a senior coordinator right from the beginning. In all 4 years, when we have summer workshop in the summer, he was giving talks all the time. And this year he has chosen a new topic that he hasn't talked about before. Jana, you've got about 40 minutes or so, and maybe allow a few minutes towards the end for questions. Otherwise, the floor is yours. Thank you.
Yeah, thank you, Asifa, for the kind introduction. Thank you all for being here to listen my talk. And I'm going to talk about security and robustness of time series machine learning. And this is joint work with my former PhD student, Taha Belkauza, who is now a research scientist at Accenture Generative AI Labs. So let me get started. So this is the outline of my talk. I'll try to briefly motivate the problem, and then I will talk about how we got into this problem, whether this problem is real or not, and then I'll talk about some methods to solve the problem, and then some applications that also motivated this research. So let's get started. So we have sensors everywhere from which we collect data and then use them to analyze and make predictions and decisions. So these could be smart homes, smart health, wearables. So time series data is very, very ubiquitous. And to analyze such data, you need machine learning methods. And what we are going to talk about today is that how these machine learning models operating on this time series data can be brittle, either due to natural noise in these data or through some adversarial attacks that are created by adversaries. So there are many applications of doing time series machine learning. It could be you want to classify what activities a human is doing based on the variable sensing data, or you want to basically predict some medical diagnosis from such sensing data, or you want to predict maybe future weather or stocks. Maybe you want to impute some missing data from medical observations, or maybe you are just monitoring a system and you want to raise alarms whenever there is something abnormal or anomalous thing that is happening. So you can easily see that time series machine learning is quite useful. And the machine learning models that are used to analyze such time series data, there are classical methods like ARIMA, VARMA, linear regression, and random forest-based methods. But also there are deep learning-based methods which kind of go away and kind of learn good representations from such raw sensor data. These could be your LSTMs, transformers, GANs, and inception-based time series. So there is a lot of active work on deep learning for time series data, but not as mature as compared to images and natural language data. So the time series data has many challenges. One is just the noise in the data. And how do you kind of model these structure, both space and time, when you have multiple uh, you know uh, multivariate signals, and also there are basically some correlations across space and some correlations across time, and you want to capture all of them to be able to make good predictions, right? And the main problem that we are going to actually address today is when somebody deliberately tries to change this time series data, then the machine learning models can fail very, very badly. So, for example, it could be like for a health application, you might be predicting something very, very bad happens, even though if it is pretty much normal. Or if you are making some decisions about smart grid, and if you rely completely on machine learning predictions, it could also lead to some very bad outcomes on the smart grid example, blackouts. So let me start off with a basic example of what an adversarial example is. So this is a very, very well-studied problem in the context of images and to some degree on natural language text. But when we started working on this problem on time series modality, this was a completely, unexplored problem, and that's why we got started. So let me start off with this example. So here, let's say, you're looking at an image and you're trying to predict, whether this image corresponds to a normal or a malignant tumor, right? And the machine learning model is doing fine, as you can see if you look at the original image, and its confidence on being normal is actually very, very high. And then here they randomly try to inject basically some noise into this image. And if you look at this image on the right hand side, it exactly more or less from a human perspective, they both look very, very same. But now if you ask the machine learning model, it is saying it is completely confident that it's actually a malignant tumor. Okay. So for a human eye, these two both look the same, but with some amount of noise, the machine learning model's prediction completely changed, right? And you could imagine a same scenario with time series data as well. So you look at the time series data, add some noise to it, and you get basically an adversarial example. And the main issue, the main challenge in not being able to use the same technology that we have developed when it comes to images to time series is that unlike the images, the time series signals are not interpretable by human eyes. That's actually one of the main challenge that we are going to address. Um, yeah, so like I mentioned, there is this noise, and there is also natural noise, right? So this could be due to sensor miscalibration, or when a person is wearing wearable sensors, and maybe the orientation of the sensor changed as a result, the observations changed, right? So these are some natural perturbations, and that's why in my title I had both security and robustness. So when it comes to natural perturbations, it's not like really a security challenge, it's more a robustness challenge. And then we also have adversarial examples, right? So what we did to begin with was we first wanted to understand whether this is actually a real problem or not. So that was one of our first explorations when we said, well, let's see if this adversarial thing really makes sense. That means that if we create some adversarial examples on the time series data, can the machine learning models fail just like the image examples that I have shown? And nobody has done that. So we had to do that to convince ourselves that the problem is real before we try to kind of solve it, right? So here is a very simple cartoonish picture where you have basically a bunch of sensors. Every sensor is actually sending a bunch of data. So this is kind of a univariate signal from each of the sensors. And basically what we are saying is that this orange colored sensor is kind of vulnerable. It's compromised by an adversary, right? So as a result, the signals that you are getting from this orange sensor is kind of tampered, right? Everything else is normal, and you can easily think about, okay, there could be multiple vulnerable devices and there could be multiple tampered signals among your multivariate sensor data. And then you give this to basically a deep model, whatever it could be. Here it is basically a one-dimensional convolution neural network, right? Uh, so what we wanted to basically see was, well, can we come up with these worst case scenarios within a threat vector that we define? And can these adversarial examples fool the deep models? And can we create good data augmentation techniques to improve the robustness of the deep models against such adversarial examples? So that was the motivation for us, right? So in this context, I'll quickly go over. There are two kinds of attacks. One is called single instance versus universal attack, which basically means that you kind of figure out one noise pattern that would work for all inputs. For in the case of images, you have this one noise pattern that you would apply uniformly to all the images, right? On the other hand, for a single instance, you would basically say, for each input and for this model, I am actually going to find one optimized adversarial example. Okay, so that's the difference between universal versus a instance specific attack. And the other kind of dimension in adversarial attacks is what do you assume about the machine learning model, right? So the black box scenario basically says that you only can query the model by passing an input and observing the output, and you don't know anything that goes on between in the middle, right? And the white box says basically, you know the model, you can actually, derive the gradients and so on and so forth, and observe basically the entire process of making the inference from input to output, right? And you can easily imagine the black box scenario is much more harder compared to white box because you have less information. So here I'm going to basically show you the threat vector. So from an attacker side point, how does it look like? And from a system pipeline point of view, how does it look like, right? But essentially, you need some ways to, create or tamper basically the signals by making these devices vulnerable. This could be, attack over the hardware nature of the sensor, or it could be just a wireless attack once the signal gets passed from the device. So the main issue, as I mentioned, there are two things. So unlike the standard regular images, time series is very, very difficult. Fast, partly because you could have fast-paced oscillations or sharp peaks. And like I mentioned, the time series data is not interpretable from a human perspective, right? So we don't even understand what is a real signal versus what is a perturbed signal, for example, and how to make the difference out of them. The other problem is that when you create adversarial examples, sometimes the adversarial example could be a natural time series signal corresponding to a different class label. And you would not know. Again, it is due to basically the lack of interpretability with this particular data. So that's actually one more challenge. So as like I mentioned here, for example, you created a perfect adversarial example, but now this is actually a perfect example from a different class. So it's very, very similar to an example that comes from another class as opposed to being an adversarial example. So now, how do you differentiate between these two scenarios? So that's actually one big challenge. So the standard, there are actually tools to solve the adversarial machine learning problem in the images. And here is actually one common approach where, you pass on an input and you say that, well, I have certain bound over how I create basically my adversarial examples. That's the delta bound. And then you basically say, given this classifier, I want to create an adversarial example which is actually very close to the original input, which is within the bound delta, right? So you can use basically whatever distance function that you use. In the standard image cases, you would use basically an LP norm. When P is 2, it's actually Euclidean distance. And you want the classifier to predict actually a wrong class label, let's say Y target, even though the original class label is, let's say, Y. So that's basically a very targeted attack. And the main component that we don't know here how to do is, what does a good similarity function mean in the context of time series? Because in the standard images, people have used LP norm, L1 and L2 and L infinity. But in the time series case, we don't know if those are actually useful or even make sense given the challenges that I mentioned, right? So we will talk about two approaches. One basically which can capture this kind of differences between the different time series signals, and another one, you have very, very, very similar, but there is a slight time shift, temporal shift in the signal, right? And you need different kind of techniques to handle these two different kinds of similarities. Okay. So the first approach that we kind of started talking about was, well, in the literature of time series analysis, it was found that statistical features over time series helps with the interpretability of time series. Okay, so then we started off with that hypothesis and assumption, and then we said, well, why don't we actually constrain the values of these statistical features. So if you look at the original time series signal and the adversarial signal, we want to bound the difference between the corresponding statistical features over these signals, right? So that was the basic thing. So you're using statistical features as another representation of the time series, and you're trying to measure the difference between those statistical features, right? And the rest of the story is essentially same. And then the other twist that we kind of thought was we will use basically what is called a polynomial transform over the time series signal, and the linear transform that we typically have in the standard adversarial example would be a special case here. And we have a theorem that basically says that by using a polynomial transform, we are actually increasing the space of the adversarial attacks compared to the standard additive perturbations. It's very easy to see that because it's a special case of it. And then the main question that becomes here is that, okay, now you have a framework which basically says you can use basically statistical features. Now, which ones you want to use and when? So we have two kinds of scenarios. In a domain agnostic manner, we kind of used some standard statistical features like mean, kurtosis, skewness, and so on and so forth, which are very, very well known in the time series machine learning literature. But even when we are trying to apply this algorithmic framework to practical applications, for example, when we were trying to classify activities from variable sensors data using accelerometers, we kind of used some specific features that makes more sense for that particular application. So the framework is general. It's basically if you have some additional domain knowledge about the application, so you want to make use of it. So let's look at basically, from a qualitative assessment point of view, what does these statistical features do, right? So here I'm showing you the data. This is the TSNE plot of the original time series signals, which are in the blue points. And this PGD is the data corresponding to the adversarial examples created by a known attack called projected gradient descent. So as you can see, the examples that are created by PGD are actually highly dissimilar to the blue points that you have. Whereas the orange points are the examples that are created, the adversarial examples that are created by our statistical features approach. And you can see that they look more and more similar to the original ones compared to the green ones, right? So this kind of is a qualitative measurement to basically show that the existing similarity metrics that are used within the image domain are not applicable here precisely. And then here I'm showing you that, so here you have some attacks. So this is Carlini-Wagner, projected gradient descent, and fast gradient sign minimization. So these are three attacks. And then we have white box and black box attacks. So essentially here we are saying, let's use basically the existing attacks and see how much they can fool the deep learning models. Okay, so that's what these results are. And as you can see that you can fool them to varying degrees, and of course you can do the best when you have a white box attacks because you have the complete knowledge about the setup. And then we kind of said, well, okay, now we have the baselines. We have the Carlini-Wagner projected gradient descent and FGS-based adversarial examples, and we have the clean examples, right? So when you have clean examples, you will do the best. And then you have this TSA stat, which is our approach, right? And you can see that when you augment the data using the adversarial examples created by each of these adversarial methods, then the TSA stat actually stays much more closer to the ideal setting compared to the others. So the green bar and the blue bar are more or less similar, which basically shows that the adversarial examples created by TSA stat are actually much more faithful to the domain, and that's why the robustness of the classifier kind of improves. And we also have some certificate guarantees. So in general, when it comes to this safety with respect to adversarial examples, you kind of want to say that, okay, what are the conditions under which, the your classifier is robust? These are called certificates. And we actually give certificates for our particular attack. And in the interest of time, I'm not going to go over them. I'll move on to the second approach, which is the temporal shift. And, dynamic time warping is actually a very popular measure that is used within the time series community to kind of look at such temporal shifts. It's very, very natural for us to look at it, right? And so we started looking at it and we ran into some problems, right? So here essentially you're kind of measuring using dynamic programming, like what is the similarity between these two different time series, right? So and the main problem here is that if you want to measure the dynamic time warping measure between an input X and another input S, because you have to solve this dynamic program, it's actually a quadratic complexity and it's actually very, very slow. So if you think about the overall framework, it's an iterative approach, right? So you have to keep calling this DTW measure over and over again. And that makes the problem of creating adversarial examples much, much, much slower. And we'll talk about basically one good insight that actually gives us a handle of addressing this time complexity issue. And before that, just like the example that I have shown before, here I'm showing you the colored points are essentially the time series signals corresponding to different classes, right? And here the Euclidean, this is the TSNE plot for the Euclidean space, and here it is the for the DTW space. And you can see that in the DTW space, all the examples that are belonging to the same class are actually very, very well aligned as clusters, unlike the Euclidean space. And this is kind of again a qualitative description to basically say that the DTW measure is a good similarity metric when it comes to time series. Okay, so now I mentioned to you, the framework is same. Only the similarity metric definition is what changed. So the question is, in each iteration, if you have to compute the optimal DTW alignment, you have to run a dynamic program. And so the computational cost is very, very high because you have to do it iteratively to optimize the adversarial example, right? So that's the iterative approach. And you will only get one adversarial example using this framework. So both of these are an issue. So the main insight that we brought to the table was if you select a random alignment path and if you optimize your adversarial examples with respect to that random alignment path, the solution to that would be same as solving an optimal alignment. Okay, so, and that's what we do. So basically what we do is that we randomly select an alignment path and then solve this problem using that thing. And actually we show that it's a very, very tight approximation and we get the same solution. And the main reason is that, this path similarity metric kind of helps us optimize that. And here I'm showing you one example where how we find basically the adversarial example over iterations. As you can see that over iterations, we are actually converging and the alignment path that we found is actually optimal, even though we are not solving for the optimal alignment in each iteration. So like I mentioned, the overall framework is exactly same as before. The only thing that changed was how we measure the similarity. In this case, we actually select a random alignment path and define the similarity with respect to that, and then we do the gradient ascent to find the adversarial examples. Okay. So here, the first thing we kind of said, well, computational efficiency. And as you can see, we compared it with basically the standard DTW. And there are basically faster ways of computing DTW. And we found that there is actually a whole body of work on that. And at that point of time, DTW was actually one of the more fastest one. And as you can see, even with respect to them, we are actually very, very fast in terms of actually computing these adversarial examples. Okay. The second advantage was that by selecting different random alignment paths, we can generate many, many, many adversarial examples. That was not possible if you were using actually an optimal alignment path, right? And that means that you are actually being exposed to more diverse adversarial examples that would actually help your classifier becomes more robust and also would generalize better to out of distribution data. So now we look at the effectiveness of the adversarial examples, and as you can see, the adversarial examples coming from the DTWAR actually leads to the most loss, which basically means that this is actually a very good algorithm to find better adversarial examples. And then we were also able to improve the accuracy by adding them those adversarial examples. So those are the main results. So far, what I have talked about to you was that adversarial examples in time series is a real problem, but we cannot actually use the existing methods on images to time series directly because we don't know how to measure the similarity between time series. And then I showed you two different instantiations of the same framework where we use two different similarity measures. One where we used the statistical features of time series, and the second one we used basically a dynamic time warping measure. Now let me try to go back and say, well, can we use these frameworks to solve some real applications? And we actually did that with one of our collaborator, Ganpati Bhatt, who actually specializes in variable enabled mobile health. And one thing that we have thought was, well, okay, when variables are being wore on the person's body and when they are moving, their orientation can actually change, and that can lead to disturbances in the data, and the ML classifiers can actually perform very, very bad. So we investigated, some sensor disturbances like, heading rotation, pitch rotation, amplitude disturbances, right? And then we wanted to see these are all very, very natural. So how does so this is nothing. This has nothing to do with adversarial. I mean, if you somebody is doing also adversarial, that will be actually on top of it. But here we were actually dealing with natural sensor disturbances because of, the orientation change and so on. So we basically applied the same TSA stat algorithm in this particular context, and we actually showed that using the TSA stat based adversarial examples, if we train the classifier, then the classifier is way, way more robust compared to when it was not trained using the standard clean data. Okay. And then we also showed that the implementation overhead for this whole method is actually very small on a real device. Okay. And another application that we considered was about how to deal with missing data. So let's say a sensor failed, or either because of some reason, or whether because it ran out of power. How do you deal with filling that missing data, right? And then there were two main insights in solving that particular problem, which was uh, basically to say that you know, our goal is probably not to impute the data exactly like the original one. As long as we can impute the data such that, the classifier or the machine learning model would make the same prediction as if we were given like the complete time series signal, we are good. Because our goal is not to, impute the data exactly, right? So with that, because we wanted the data to be imputed so that the machine learning model can actually work well in the context of the application, right? And at that point, because when you're imputing the data and there could be some changes here and there because you're not exactly exact, you want the classifier to be robust with respect to that. Okay. And we already saw that the TSA stat is actually a very, very good framework to create reliable classifiers with respect to the imputation, right? So both a reliable classifier and these imputation patterns kind of help us solve the imputation problem in a very, very efficient manner. So we actually don't do much computation. We actually store some imputation patterns on our device. And whenever we basically see that, okay, this is the missing pattern, we will actually look at the lookup table and actually add one of the appropriate pattern for that data. So that's why there is no overhead at the runtime. And this actually method works really well. And again, like I mentioned, it's only the storage that is the cost. There is no actual real computational cost on the device when you are trying to impute the data. The last piece of work that I'm going to kind of talk about briefly is how to train robust deep models for time series domain. And these could be applicable both for natural disturbances or the adversarial ones. So far, the way to create robust deep models, what we did was we used a machine learning model and the data to create adversarial examples, and we augmented the existing training data with these adversarial examples, and then retrained the machine learning model both on adversarial examples and the clean data. So it's kind of a indirect way of actually doing that, right? So let's try to look at a direct approach to solve this particular problem. And you can actually formulate this as a min-max optimization problem where the inner max is basically trying to say, let me find the worst case examples where the classifier is failing. And then the outer min is trying to find, okay, with respect to the worst case errors, can I find a model that minimizes my loss? In fact, the adversarial training approach that we talked about before is kind of solving this particular problem in an approximate way. Now we are trying to solve it in a much more direct and exact manner. Okay. So here we kind of looked at a global alignment kernel as a similarity measure which is defined over all possible paths, right? And that's what the main challenge is. Like I mentioned to you, the inner maximization problem is served by the attacker, and the outer maximization is kind of the defender. And you have this distance measure between the original signal and the perturbed signal using this global alignment similarity measure. So there were few challenges because it's kind of an optimization problem and you have to try to learn the parameters. The main challenge was that the gradient estimation is computationally expensive, right? So for that, what we did was instead of looking at all the paths, we actually sampled a subset of the paths at each iteration and computed a biased gradient estimate using that. Okay. Um, yeah, so like I mentioned to you, when we were trying to solve this particular problem, there was no existing solution for this kind of a problem, which basically has this kind of a compositional structure. And fortunately, my colleague Jan, who had actually a lot of optimization expertise in min-max optimization, he brought some new tools to bear to solve this particular optimization problem, right? And the main idea was that instead of requiring all alignments, we basically sample a subset. It actually is efficient for training and improves scalability, especially for large scale data. And we had some theoretical results, and the empirical results also match with the theory. So one is that it converges faster, right, which we are showing on the left hand side. And also we showed that the accuracy gap in the gradients over the weights and over the perturbations actually go down as actually the iterations progress. So in every iteration, you're only using a small subset of the alignment paths, but over time, this gap actually is kind of going down because it gets amortized. And then the runtime is actually negligible compared to, using all alignment paths. And just like the setting that we talked about before, if you use adversarial training versus our approach, we do better in terms of the model accuracy. And similarly, we did an ablation on the distance measure because the framework is general enough that you can plug in basically either a Euclidean distance or the GAK. And we saw that the GAK is a much better similarity metric compared to the Euclidean distance, and which is kind of the message that I have been giving throughout the talk. And the other one is that, there is another baseline called the stability training, and we compared with respect to that. And even with that, actually, our method was doing much better. So to conclude the talk, hopefully I'm on time. So what I tried to raise an issue is that both security and robustness of time series machine learning models is a real issue. And these could be the robustness issue could come from the natural disturbances, and the security issues could come from the adversarial attacks. And then I convinced you that this is a real problem. And then the main challenge is that we don't know, unlike images, the time series signals are not interpretable, and we don't know how to measure the similarity between two time series examples in, within the adversarial framework. And then I told you about two different methods, one that relies on the statistical features of the time series, and the second one was on dynamic time warping based framework. And then we also gave some certified bounds for the statistical features one that applies to any deep model and for any time series domain. And then I showed you some applications of how to use these tools to make classifiers robust on real variable data and also to impute missing time series data. And then towards the end, I kind of talked to you about how to train robust models using a min-max optimization formulation using a global alignment kernel. And I showed you what some of the challenges are and how we could solve those efficiently by sampling a subset of alignment paths. So with that, I'm done with my talk. I finished 2 minutes before the time that Asifa gave, so I'm happy to take questions.
Wonderful. Thank you very much, Anna. You did an excellent job with those 40 minutes and walked through very many interesting works. Let me see if you have any questions for Jana. Anyone have any? Everything was very clear. I'll ask one question, Jana.
Yeah, sure.
The statistical features you used
Uh-huh.
where people also in time series machine learning would use in the context that's maybe not as general as yours. Were they the same sort of statistical features and summaries that were used now for this guaranteed performance where
Yeah,
you
yeah,
used,
yeah, yeah, yeah.
or were
No,
they kind of specially designed for this?
no, so these were the same features. So our motivation was there was a paper that basically talked about why these statistical features on time series were makes them more interpretable. So that was the main hypothesis where we started with this particular framework, right? And then we basically used whatever features that were listed actually in that framework. But we also had an approach where we basically said, well, okay, which subset of the features you should be using, right? So
Right.
can actually iteratively in an optimization loop kind of add which subset of the statistical features that would be a particular domain. In fact, when we submitted to JIR, one of the reviewer asked that question, and as a result of that, we said, well, okay, this is an important question from a practitioner's point of view, so let's try to
Right.
address it. So we have an approach to select from a given subset of statistical features which ones you should be using for a particular domain.
Nice. That's excellent. That's great. Any questions? No. Right. So let's thank you.
All right, thank you all. Yeah,
Thank you very much.
yeah, bye.
Bye.